All right, friends, we'll go ahead and begin. Welcome back and happy Inauguration Day. I have some opinions which I will not share with you, but if you want to come talk, I'm happy to talk. Not in class, but yeah, happy Inauguration Day, great celebration of peaceful transfer of power. All right, so we're going to continue our discussion of HOMO versus LUMO with the goal of being able to predict how organic molecules react. And hopefully by now, as you've been working on the study guide, you have gotten good at drawing the HOMO and the LUMO of an organic molecule if given to you. And one of the things that we've learned, and I think I tried to mention this last time, is that there are some types of orbitals that are more likely to be the HOMO or more likely to be the LUMO than others. For example, the sort of lowest energy bonding orbitals we've considered have been sigma bonding orbitals perhaps between two carbon atoms or a carbon and hydrogen, maybe carbon-oxygen or a carbon nitrogen sigma bond. And those are very low in energy and are almost never the highest occupied molecular orbital. And so because of that, even though it's not true that those sigma bonds are identical in energy, we can pretend they are because they're almost never the HOMO. So we're almost never going to have to decide, oh, is this carbon-carbon sigma bond higher or lower in energy than a carbon-hydrogen bond? Isn't really going to be that relevant for us because there's usually always higher energy orbitals to deal with. There are, however, a class of sigma orbitals that are associated with weak sigma bonds, and that would be, for example, bonds between carbon and chlorine, carbon and bromine, carbon and iodide, perhaps carbon and, say, an oxygen that has a positive charge on it. This doesn't include carbon and fluorine. Carbon fluoride bonds are actually very strong. Now, we haven't talked about why these bonds are weak. You can look up their energies in a table at the back of your text. We're going to learn some reasons why they're weak in Chapter 2 and later on in Chapter 7. But for right now, you can just take as fact that they are weak. And a weak bond means that the sigma bonding orbital is not that low in energy. And that also means that the sigma star associated with those weak bonds is not that high in energy. Nevertheless, notice that for most of these cases, with these weak sigma bonds, most of them involve heteroatoms that have lone pairs. So these are also almost never the HOMO because when they are present, you probably have lone pairs in the molecule, and that's going to be the HOMO, right? And then somewhere between the lone pairs and the weak sigma bonds, you have the pi bonds, carbon-carbon, carbon-nitrogen, carbon-oxygen. All of these have electrons in them. And I guess in green, I will highlight all of the orbitals that are bonding orbitals. It isn't going to be really an issue in any organic molecule that we'll deal with. For example, having to choose between a pi orbital versus a weak sigma bonding orbital. Because, as I said, anytime you have one of these weak sigma bonding orbitals, usually there's a lone pair on the heteroatom. So for identifying the HOMO of organic molecules, you sort of want to look here. Look for lone pairs or pi bonds. I guess in yellow, I will highlight the area of our energy diagram that sort of represents atomic orbitals, non-bonding atomic orbitals. This is our break-even point, the sort of energy level where we started before we made bonds. These are our bonding orbitals. Also showing up in this region is the empty p orbital. Again, it's an atomic orbital, so it's about at that energy level. And this is about as low as you can get and be an empty orbital. So if you've got an empty 2p orbital, that's the LUMO. A little bit up from that would be the pi star associated with a carbon-carbon, carbon-nitrogen, or carbon-oxygen pi bond. Similarly, we would have sigma stars for weak carbon chloride, carbon bromide, carbon iodide, perhaps carbon bonded to a positively charged oxygen. Just as we will never really have to worry about whether about the relative energy level of these weak sigma orbitals versus pi orbitals, so you're almost never going to find a situation where you've got to choose, oh, is the LUMO this sigma star or is it the pi star? Many of the molecules we'll deal with will be fairly simple. They will have one reactive location. If you encountered a molecule that had both of these, maybe you would learn that it was reactive at multiple spots. And then we'd have to develop some other strategies. But again, and what I will ask you to do for this first exam, you're not going to have to worry about, is the carbon-carbon pi star lower or higher in energy than a carbon-chloride sigma star? I don't actually know. You could look it up or you could do the calculations and figure it out, but it's not something that I need you to be able to do. And then up here, highest in energy are the sigma stars associated with our strong sigma bonds, carbon-carbon, carbon-nitrogen, oxygen, carbon-hydrogen, carbon-fluorine, and so on. These are almost never the LUMO. So when trying to identify the LUMO, you want to look here, starting probably with the empty p orbital and then pi star and sigma star. And I guess I'll highlight in red that these are all anti-bonding types of orbitals. Yikes. Needed a bigger crayon there. Oh well. All right. Okay. So that's sort of a summary of how we can think about HOMO and LUMO inorganic molecules. And through much of 351 and 352, this will be how you can identify where a molecule is reactive. In Chapter 3, we're going to learn about functional groups. And some people prefer to think about reactivity in organic molecules by thinking about the difference between an alcohol and an ether versus a ketone or an aldehyde. If you master HOMO and LUMO, you almost don't need to do that because the structure itself is enough information. All right, any questions anybody wants to ask at this stage? Okay, yeah, and then there. Go ahead.
So the MT2 orbital is like, for example, there's a molecule that, like the central carbon or like element, if it can bond to more things, but there's no pairs, is that what it is an MT2 orbital?
Yes, the question is, do you find an empty 2p orbital in a situation where an element has a space for more bonds and doesn't have a lone pair there? Yeah, that's a pretty good summary. One case in which there's an empty p orbital would be, say, this carbocation, and just as you summarized, with a positive formal charge on that carbon, I know the carbon's only surrounded by 3 groups. I know that it has to therefore be trigonal planar sp2 hybridized. And I know that the sp2 orbitals, the 3 sp2 atomic orbitals on carbon, are each part of these sigma bonds. So what's left over is that unhybridized 2p orbital on carbon that where the wave function, the sign of the wave function above and below the trigonal planar carbon is opposite. So yeah, another example would be boron type molecules that we've maybe alluded to either in office hours or in class previously. Boron also is surrounded by only 3 groups without lone pairs, and again, you come to the conclusion that it's got an empty p orbital on it. And we'll focus mostly on, for empty p orbitals, on those second row elements, boron, carbon, and in fact, those are the boron and carbon are sort of the main ones where we will find that. Okay, yeah.
Yeah, we've seen a few examples where we use what we know about generating orbitals to generate multiple pi orbitals. So can those all be assigned antibonding or bonding orbitals, or some of them just not assigned that way?
Oh, okay, yeah. So we've talked about systems like the allyl anion where you have multiple pi orbitals. Just to answer, and the question is it possible to tell which of those pi orbitals is bonding versus anti-bonding? It is. I don't foresee myself asking that question at this stage, but there is an answer, and it's not that hard. If you remember, there were 3 pi orbitals for this system. There was one, the highest energy one looked like this with 2 nodes. The lowest energy one looked like this with 0 vertical nodes. And the middle one had a single node that corresponded to the position of carbon 2. To determine whether an orbital is bonding versus anti-bonding, you count the number of times the wave function is the same sign on adjacent carbons. Okay, so I'm counting 1, 2, sort of 2 times that we have the same wave function sign on adjacent carbons. Here, for the middle one, it's 0 times because the wave function is not on adjacent carbons here. So, and then for the top one, we would say, actually, there are 2 times where the wave function is opposite sign, or I suppose we could say there are -2, I don't know, 2 times where the wave function is on adjacent carbons with opposite sign. You can think about any time the wave function's on adjacent carbons with the same sign as being a bonding type of situation versus an anti-bonding situation. So pi 1 has 2 bonding situations. It's a bonding orbital. Pi 3 has 2 out of phase situations, so that's an anti-bonding orbital. And pi 1, though it does have a node on carbon, it's not on the switch in sign is not on adjacent carbons, and so we would actually call this a non-bonding orbital. So there is a way to do it. It's not essential for this stage, but that's how you think about it. Okay, what else? Okay, well, let's now embark on the wonderful world of organic chemistry and reactions. And to do this, you need to know the first and great commandment of organic chemistry. And that is, and this is the theme of 351 and 352, nucleophiles attack electrophiles. That's how reactions happen. And the second commandment is like unto it. Is this blasphemy? I hope not. We're just alluding to connections here and there. The second is like unto it, and that is that HOMO attacks LUMO. Highest occupied molecular orbital on the nucleophile attacks the LUMO of the electrophile. if you keep that in mind, and if you are good at identifying HOMO and LUMO, you will be able to predict with startling accuracy the outcome of reactions that are unfamiliar to you. So to illustrate this, I'm going to show you a few different situations. Some of them are going to be from chapters way later on in 352. One of them is going to actually be, 351. One of them is actually going to be from 352. And I hope to demonstrate that with your knowledge of HOMO and LUMO, you can have a pretty good idea of what's going to happen in the reaction. A first example of these two great commandments is the situation where the HOMO is a lone pair on our nucleophile, and the LUMO is an empty 2p orbital. So a classic example of this is to say if we had BF3, which we've already identified as a molecule that has an empty p orbital. I will tell you right now that BF3 is the electrophile. During the last class, students asked, how do I know whether something's an electrophile or not? The answer is, for right now, I'm going to tell you. But in general, electrophiles are molecules that have low energy LUMOs, whereas nucleophiles are molecules that have high energy electrons, high energy, highest occupied molecular orbitals. So if a molecule has an empty 2p orbital on it, that's about as low as you can get for a LUMO, so it's a good bet that it's an electrophile. We'll get better at that, especially after chapter 2, but for right now, you can accept the fact that I tell you this is an electrophile, and therefore we care about what the LUMO is, and as we just noted above, it is the empty p orbital on boron. Our nucleophile here is going to be a molecule called diethyl ether. It is the bat molecule, not because it comes from bats or has anything to do with bats other than if you draw it like that, it sort of looks like a bat. Maybe an upside down bat, if we put one of the lone pairs, can be fangs or something. Anyway, sorry, it's way less funny now that I just pursued that. So we'll just, moving along, this is our nucleophile. Therefore, we care about what the HOMO is, and in this case, it's the lone pairs on the oxygen. You can think of those lone pairs as being in an atomic orbital of some kind. We could think of that oxygen maybe as being sort of sp3 hybridized, so maybe that lone pair is in an sp3 orbital. If you want to think of it as being in a p orbital on oxygen, that's fine too, doesn't matter. Now that we've identified HOMO and LUMO, we're going to take an arrow and start with the electrons in the HOMO, and then we're going to draw the arrow to where the LUMO is. The arrow is going to end with the nucleus where the LUMO is, in other words, boron. And this is dumb, but I'm going to do it anyway. We're going to pretend some animation here. HOMO attacks LUMO is going to involve end-on-end overlap of HOMO and LUMO. Shoot. Okay, so you saw sort of, there we go, delete. End-on-end overlap generates sigma bonds. So we're going to make a new sigma bond between oxygen and boron. And conceptually, you can think of this bond as coming from the empty 2p orbital on boron and the lone pair on oxygen. They're going to mix together via end-on-end overlap to create a new sigma bonding orbital and a higher energy sigma star anti-bonding orbital. We can draw the product of that reaction. The electrons in that lone pair end up in the sigma bonding orbital. Let's draw the product of that reaction, a new bond between carbon and oxygen. Nothing else about the molecule's bonds changes, so oxygen has to have a positive formal charge. It had 2 lone pairs, now it's surrounded by 3 things with 1 lone pair, positive formal charge on oxygen. Boron is now surrounded by 4 groups, so it has to be tetrahedral and sp3 hybridized, and boron has to have a negative formal charge because it normally comes with 3 electrons but currently owns 4. That's the new sigma bond, and we get it from HOMO attacking LUMO. Questions? Yeah?
On the diethyl ether, are there supposed to be 2? Oh, I see it now.
Yeah, on the diethyl ether there, the question is, are there supposed to be 2 lone pairs? Yeah, you don't actually have to draw lone pairs on atoms. I draw them for emphasis, and so that's why I left out 1, but then put it in later on in the end. Other questions? Anything on the chat that I'm missing? Okay, yeah, so the question is, what is the difference between a nucleophile and an electrophile? A nucleophile is electron rich, and it has a high energy, highest occupied molecular orbital. Electrophiles are electron poor. They are Lewis acids. And they have low energy LUMOs. We'll get better at recognizing nucleophiles or electrophiles. Right now, what you need to know is if something's an electrophile, you care about what its LUMO is. If something's a nucleophile, you care about what the HOMO is. All right, yeah?
Does that new bond that you formed between the oxygen and the boron change the orientation of the other bonds as well?
Does that new bond that we form between oxygen and boron change the orientation of the other bonds as well? Yeah, boron used to be trigonal planar, and now that it's got 4 things, after this new bond, it's surrounded by 4 things. So according to valence shell, electron pair, repulsion, Vesper, it's got to rehybridize and become tetrahedral. So it's almost like those fluorines, which were laying flat, pop up kind of like an umbrella going inside out. Yeah, so forming that new bond does have an effect on the structure of the other things that are bonded to boron. Yeah, yes?
This is kind of a 105 question, but I'd like to hear it from a bookend perspective.
Okay.
So they both have formal charges, so how is this actually favorable?
Okay, the question is, these atoms both have formal charges, so how is it favored? Remember that formal charge is just about electron counting. It may not tell you that much about the actual distribution of electron density in the molecule. So why is this favorable? Well, because it allows the lone pair electrons on oxygen to move lower in energy. Now, the formal charge says boron has a negative charge on it, but look what it's surrounded by, electronegative elements. So probably that negative charge is spread out onto each of the fluorines and onto the oxygen. If you wanted to do quantum mechanical calculations, you could estimate how much of that negative charge is at various positions there. Yeah, so you have to be somewhat careful about interpreting formal charge because it's mostly just about counting electrons. Bonds are stable when the electrons in them are lower in energy than they used to be, I guess is a way of summarizing it. Okay, yes?
Just a clarification, does the MT2P become sp3 hybridized as soon as it...
Yeah, does the empty 2p orbital on boron, what happens to that? Well, I suppose we could imagine to ourselves that when we make this new bond, the electrons on the lone pair end up in the sigma bond, And I guess that would mean that the empty 2p orbital ends up as the sigma star. Yes, that boron does rehybridize. So yeah, after the reaction, the empty 2p orbital isn't there anymore. You would have the oxygen boron sigma star in its place. Yeah?
So with the ethyl groups and the diethyl, does it matter? It seems like which direction they're facing, if they're facing in towards the boron.
Oh,
Does that matter?
yeah, the question is, does it matter where I draw these ethyl groups? Does it matter that I've drawn them pointing towards the boron? No. We will see as we get to chapter 4 that sigma bonds you can rotate freely around, and so actually at room temperature there's enough energy, there's enough kinetic energy of the molecules at room temperature that those bonds are rotating like sort of crazy, and so this methyl group, I could just as easily have drawn it here. Yeah, and we'll deal with that more in chapter 4. Okay. So there's another example of this that we talked about carbocations above as having empty p orbitals. I'm not going to go through this in a huge amount of detail, but this is an example of the same principle. It's a reaction from chapter 7. It's called the SN1 reaction, and it involves an empty p orbital on a positively charged trigonal planar carbon being attacked by, say, non-bonding lone pairs on some heteroatom. In this case, we'll say water, and HOMO attacks LUMO. We basically do the same thing. We're going to make a new oxygen-carbon sigma bond. And the principles are exactly analogous to what we did above with boron. All right. Situation 2 is we're going to stick with lone pairs as the highest occupied molecular orbital, but we're going to have that, instead of attacking an empty atomic orbital like a 2p orbital, we're going to have it attack a sigma star for a weak bond. Let's just say it's a carbon-bromine sigma star. I'm not sure. This example we may have done it in office hours, or we may have done it in the study guide. In any case, I'm going to draw this molecule, which is called ethoxide. It's the conjugate base of ethanol. It is our nucleophile. I'm just telling you that that's the case, and you can accept it because I said so. If you're like my children and because I said so is not a satisfactory answer, then for now the fact that the oxygen is negatively charged can tell you that this molecule at least has extra electron density, so it's not a huge jump to think of it as electron rich or a nucleophile. In chapter 2, we're going to learn how to recognize good nucleophiles. The HOMO then of this nucleophile is lone pairs on the oxygen. The methyl bromide is an electrophile. It's okay if you don't recognize it as such. The LUMO here has to be what? I have 4 different sigma stars. It's got to be, oh shoot, I already told you the answer. Sorry. Objection, Your Honor, leading the witness. Asked and answered. Fine. So the sigma star for bromine, in order to draw it, you sort of have to know where the sigma bond comes from. So the sigma bond between carbon and bromine comes from an sp3 orbital on carbon plus some orbital on bromine. Bromine's what? 3/4 row element, so maybe we could think of that as a 4p orbital on bromine, adding to an sp3 orbital on carbon. And then the out of phase combination we're going to get by destructive interference. So if we were to have an sp3 orbital on carbon overlap with a p orbital on bromine, the bond that we make is going to look just like that, basically, where carbon is here and bromine is there. In contrast, for the sigma star, we're going to have small lobes pointing towards the node. They are small because the wave functions have opposite sign there and have canceled each other out near the node. And there are larger lobes going in back of the two atoms with the following switches in wave function sign. So there's a switch in wave function sign at the carbon nucleus, there's a switch in between, and another switch there. This is the less stable option, the out of phase option. In the sigma bond, there's only two nodes or two switches in phase, and that neither of them are in between the two nuclei. Okay, yes?
So how do we know whether or not the HOMO wants to go into the antibonding orbital on the carbon or the bromine?
Okay, great question. I was actually going to ask that. So how do you know, the question is, whether the HOMO is going to attack at the carbon versus attacking at the bromine? Okay, and the answer is you don't yet. And we'll learn some principles for determining that. So I'm going to give answers in various levels of because I said so, and we'll get to the principles later. The first is that if you do the math and calculate how much of the wave function is on carbon versus bromine, there's actually more on the carbon. So that means that it would be easier to attack carbon than the bromine. Second would be to consider the difference in carbon and bromine in terms of electronegativity. Bromine is actually not that electronegative, but it's still a little bit more electronegative than carbon. So electronegativity would tell you that the electron poor part of the molecule is not the bromine, but the carbon. So in terms of like charges repel and opposite charges attract, you would predict that our negatively charged nucleophile would tend to go more to the carbon than the bromine just because of that difference. Finally, you could consider the relative stability of the new bonds you would make if you attacked at one location versus the other. So let's just start by saying, okay, oxygen attacks carbon. We're going to make, and that as above is going to be end-on-end overlap. So that's going to be a new sigma bond. So we would make a new carbon-oxygen sigma bond if we attacked at carbon. What would happen to the electrons in the carbon-bromine sigma bond? We're filling an antibonding orbital, the carbon-bromine sigma star, so we've got to break the carbon-bromine sigma bond, but where do the electrons go? What would be wrong about them going back onto the carbon? Okay, it's something to, go ahead. Yeah, that would be a blatant, flagrant violation of the octet rule, right? You would have 10 electrons on a second row element, which we don't do. In part, that would mean in order for that to happen, you'd have to populate an antibonding orbital. But for right now, you can think, okay, we're going to break the octet rule if we do that, so can't do that. Electrons have to go on the bromine. Then both partners still have an octet after the reaction. Okay, so the product, if we attacked on carbon, would be a new sigma bond between oxygen and the carbon. And then the other product would be Br minus. Okay, so we would, what we're going to think about is how stable is the bond we just made and how stable is Br minus versus the alternative. If we did the alternative, we would make a new bond like this, and then we would have the other partner would be the negatively charged carbon. Do you sort of see where that would come from? It turns out that if you look at this bond, oxygen bromine bonds are very, very weak. Because they're both electronegative, I think maybe. I guess I don't have a good answer for that, other than if you look it up, it's weak. You can think of that maybe if they're both electronegative, then they don't share electrons quite as well. It may also have to do with the difference in size between oxygen and bromine. In any case, that molecule there is way more reactive than bleach, and so would fall apart pretty quickly. In addition, a negatively charged carbon is very unstable. So your two options if you attack on bromine lead to a very unstable consequence, whereas an oxygen carbon sigma bond is strong, and Br minus is actually very stable on its own. You may not know that, but saying that Br minus is very stable on its own is the same thing as saying HBr is a strong acid. We're going to talk about that in chapter 2. So there are some ways you can reason your way through it. And we'll develop all of those before we return in detail to this reaction, which is called an SN2 reaction. It's actually from chapter 7. Okay? So it's okay right now if you don't know that you should attack that LUMO on carbon versus bromine. But you can see that by at least considering HOMO attacks LUMO, you could come up with what the options were and then start to try to think about which would be best. Any questions you want to ask about that? Yeah, go ahead.
So I want to clear this up. So in the beginning, you showed us when the HOMO attacks the hybridized LUMO, because there was, like I said before, there were more electrons that boron could have taken. And in this example, since the valence shell of carbon is completely full, it would have to attack the sigma star.
Yes, so you were noting the difference between example 1 and 2. Above, the electrons on oxygen were just going to a spot on boron that was available. If you just want to look at the Lewis structure, you could see that boron here is surrounded only by 3 things. It doesn't have a full valence shell. Another way of saying that is it's got an empty atomic orbital. In contrast, if you look at our electrophile here, this carbon has a full octet. There's no extra space for electrons to go. So the nucleophile has to dump electrons into an antibonding orbital or a sigma star, and that's why we got to break the carbon-bromine bond. Okay, good.
Sorry, also one more thing.
Yeah.
I didn't get how you filled in 4 electrons for the boron, and then when you mix the BF3 and the other one from the first example, is it, why are there 4 electrons?
There's only 2. The question is, why are there 4 electrons here?
Yeah.
I'm sorry, this is before the reaction, and this is after in the middle. In other words, doing the reaction allows these electrons to move lower in energy.
Okay. And by 2 is just because the lone pair.
That's right, yeah. Lone pair before becomes electrons in the sigma bond after.
Okay.
All right. Others? Whoops. Okay. Let's see. Principle number, or example number 3. Let's stick with the lone pairs as our nucleophile. So the HOMO will be lone pairs versus we're going to attack the LUMO of a carbonyl compound. We're going to attack a LUMO that's a pi star, an antibonding orbital. And for fun, right? Let's use our electrophile as an aldehyde. You don't know yet that aldehydes are electrophiles. I'm telling you that that's the case. What would be the LUMO? Oh, I already told you that, right? The LUMO, the electrophile, would be the carbon-oxygen pi star. Let's have our nucleophile just be, I don't know. We're choosing boring nucleophiles, but that's all right. Let's just have it be hydroxide, where the HOMO is going to just be the lone pairs on the oxygen. Again, you maybe wouldn't know that the nucleophile is OH minus and that the electrophile is the aldehyde. That is okay. But given those facts, let's see if we can predict what's going to happen. So the pi star of this aldehyde should be the LUMO. I'm going to draw sort of another plane, and the carbon of that aldehyde is trigonal planar. The three groups attached to it are all in the same plane. The pi star would have a node in between the carbon and the oxygen. We would have a lobe above the plane and below the plane on carbon, and then a lobe above the plane and below the plane on oxygen. I'll fill in the phases so you know where the wave function, where this wave function changes sign. Notice that I've shown you the lobes of this pi star pointing away from the space between the two nuclei. That's just a result you get from the calculations. A lot of times when I'm drawing a pi star, I will simply draw two p orbitals side by side and show them out of phase. That's the same thing. The three lines mean those two things are the same thing. So don't be confused by that. Another thing that I've done here is illustrated that there is more of the LUMO on carbon than on oxygen. There is a reason for that, and it's not that hard to understand, but you won't necessarily, it wouldn't be useful to you to know really until 352. So for now, you can accept it as fact. If most of the LUMO is on the carbon, HOMO attacks LUMO, where should I draw my arrow? Starting with a lone pair on oxygen. If most of the LUMO is on carbon, I'm going to draw my arrow pointing towards carbon to the portion of the LUMO that's on carbon. Again, this is going to be end-on-end overlap, so that's going to mean a new sigma bond between oxygen and carbon. Because I've dumped electrons into an antibonding orbital, I have to break the associated bond. So that means I have to break the pi bond, and I'm going to move electrons onto the oxygen. So this is very similar to what we did in example 2, only the antibonding orbital there was a sigma star instead of a pi star. Go ahead.
So just to clarify, what is labeled currently as our electrophile? Could that be the nucleophile if we were bonding with a different molecule because of the lone pairs on the oxygen?
Yes, so the question...
Comparatively of what you're like bonding with?
Yeah, so great. The question is that aldehyde also has lone pairs on an oxygen. Could those in another situation be a nucleophile? Yes, absolutely. Yeah, so for example, if you have the aldehyde with some acid, the lone pair electrons on the oxygen could attack the hydrogen of the acid. And you're going to see in many cases molecules that can be both nucleophiles and electrophiles. We're going to need to develop some tools to recognize and rank nucleophiles and electrophiles, and we'll do that. Some of it's going to come in chapter 2, and some of it we won't get to till chapter 7. So once we break that bond, here is the new sigma bond that we made. We've broken the pi bond between oxygen and carbon, and the electrons moved out onto the oxygen. And because that carbon is now attached to 4 things, it needs to be tetrahedral and sp3 hybridized. Now, some of you, go ahead.
I was just going to say, how do you know which one's going into phase, which one's
How do you know which one's going into the page versus out of the page in this situation? Just looking at this plane, the way I drew it, the hydrogen was coming out toward me and the carbon was going back in. However, you should see maybe that it would be possible for this oxygen to attack the LUMO from below. And it turns out this molecule here, this aldehyde, is planar, and both faces of it are exactly the same. So we could attack from above or below. Sometimes that kind of situation will lead to molecules that are called stereoisomers. They have the same connectivity, but their shapes are different. And that's based on being able to attack from above or below in a situation like this. Just so happens that this wouldn't result in stereoisomers, but we won't really talk about that in detail until we get to chapter 5. Yeah. Some of you may be wondering, why do we attack the carbon instead of the oxygen? The answer that because I told you that there was more LUMO on the carbon may be unsatisfying. If you want another explanation, first, realize that oxygen is more electronegative than carbon, so you predict that the carbon is the electron poor part of this electrophile and not the oxygen. So that's your first clue. The second clue is just to realize that aldehydes have an alternative resonance structure in which there's a positive charge on the oxygen and a negative charge on carbon. You may look at that and say, hold on, unnecessary charge separation and carbon doesn't have a full octet. And I will say, okay, maybe it's not the best resonance structure, but it's certainly better than the alternative where oxygen has a positive charge and not a full octet, and carbon has a negative charge. If this one is only a meh resonance structure, this one is angry eyes, I hate it, fuming, and just, right? So resonance and electronegativity tell you that the carbon is the electron poor part of the molecule, right? Okay, last example that is in your study guide, and maybe we don't have a lot of time for, so maybe I'll gloss over this, is a pi bond as the HOMO attacks a sigma star as the LUMO. So if I were to draw the pi electrons of this molecule, we're looking down at this molecule from above. A pi orbital extends over both of those two carbons. There's a lobe above the plane of the page, which is purple, a lobe below the page, which is orange. We'll call these carbons 1 and 2. The LUMO here is the sigma star between hydrogen and chlorine. We don't have time to talk in detail about how you make the hydrogen chlorine sigma star. Details for that should be included in the MO theory study guide. Electrons from the pi bond are going to attack the sigma star, and we're going to break the hydrogen chlorine bond. Again, why do we attack that hydrogen instead of chlorine? Well, just focus on the electronegativity difference between chlorine and hydrogen, and you can reason that the hydrogen is the more electron poor part of the molecule. So we're going to attack the LUMO where it is most electron poor. Attacking the sigma star causes the sigma bond to break, so our products here should be Cl minus. And then what are we going to do over here?
How do you know which one gets the hydrogen?
Yeah, the question is, how do you know which one gets the hydrogen? The answer is, in this case, doesn't matter because both carbons are identical. So even if I form the new bond with hydrogen between carbon 1 and then leave a positive charge on carbon 2, that would be the same as doing the other way. For many molecules you will encounter in chapter 10, the two carbons will be different, and I will show you how to choose which one gets the new bond. There's another possibility, which is maybe the hydrogen is equally shared between the two carbons, but that's sort of a physical organic chemistry 552 class sort of thing, so we won't worry about that here. All right, we didn't quite get to where I wanted to be in chapter 2. When we meet next time, we're going to ask what makes a good nucleophile good. And it turns out you maybe already know this because of what you learned in Gen Chem about acid-base chemistry. So that's where we'll go to next time. Until then, have a good day.